1943. Inside a roaring Detroit factory, sparks fly, steel clangs, and the smell of oil fills the air. Among the noise and chaos, workers are building a machine that would change the course of World War II. The Packard V1650 Merlin engine, also known as the V12, the beating heart of the P-51 Mustang, America's fastest and most feared fighter. But how was this legendary engine created? Every masterpiece needs a foundation, and for the Merlin, that foundation was its crankcase and cylinder blocks. These weren't simple car parts. They had to endure explosions inside 12 cylinders, at up to 3,000 revolutions per minute, for hours at a time. The process began with casting aluminum alloy. Workers melted the metal in huge furnaces, heating it until it glowed orange at more than 1,200 degrees Fahrenheit. Then, with a precision honed by wartime urgency, they poured the molten alloy into carefully prepared sand molds. The molds formed the rough shape of the crankcase and cylinder banks. Once cooled, these castings were broken out of the sand, cleaned, and sent to inspection. Inspectors used X-rays and gauges to find hidden cracks or bubbles. Even the tiniest imperfection could spell disaster at 25,000 feet. The war didn't allow for second chances. Raw castings were just the start. To transform them into usable parts, Packard's machinists had to remove excess metal and cut everything to exact specifications. Huge milling machines, grinders, and lathes shaped each surface to within thousandths of an inch. Coolant sprayed constantly to prevent overheating. Machinists bored out perfect cylinders, drilled oil and coolant passages, and cut bearing seats for the crankshaft. Jigs and fixtures held the block steady while micrometers checked every cut. Tolerance was measured in human hairs. If one cylinder was slightly misaligned, the entire V12 would rattle itself apart. Next came the crankshaft, the engine's spine. Forged from a single billet of high-strength steel, it was heated, hammered, and pressed into its rough shape. After forging, it went through multiple stages of machining to carve journals, counterweights, and oil passages. Balancing was critical. Workers added or removed tiny amounts of metal until the crankshaft could spin perfectly smoothly. At full throttle, imbalance could destroy an engine in minutes. Packard's attention to detail here is one reason their Merlins were so reliable. The crankshaft alone couldn't do much, rather it needed pistons and rods to translate explosions into rotation. Each piston was forged from aluminum and fitted with piston rings that sealed against the cylinder walls. Too loose and the engine would leak compression. Too tight and the friction would cause overheating. Getting this right was a delicate balance. The connecting rods, forged from steel alloy, were bolted to the crankshaft with precision bearings. These rods were like the arms of the engine, moving up and down thousands of times a minute. A single failure would mean catastrophic destruction. With pistons in place, attention turned to the cylinder heads. This is where the Merlin distinguished itself from simpler engines. Instead of side valves, it used an overhead camshaft system, which improved breathing and efficiency at high speeds. Machinists installed camshafts, valves, springs, and rocker arms. Each valve had to open and close at exactly the right moment. Workers measured valve lash with feeler gauges, adjusting clearances by hand. A mistimed valve would rob power or worse, cause a collision inside the engine. If one part made the Merlin truly legendary, it was the two-stage, two-speed supercharger. At high altitudes, thin air strangles most engines. However, the Merlin's supercharger compressed incoming air, forcing it into the cylinders at high pressure. This allowed the Mustang to remain powerful even at 30,000 feet, altitudes where German fighters struggled. Building the supercharger was almost like building a second engine. Workers assembled gears, impellers, and intercoolers. The gear-driven system could switch speeds, a low gear for low altitudes and a high gear for thin air. This gave pilots smooth performance across the entire flight envelope. Of course, compressed air was useless without fuel, and that's where the Bendix-Stromberg carburetor came in. Unlike car carburetors, this design had to feed fuel reliably in combat, even when the Mustang was upside down in a dive. Engineers solved this by using a special pressure carburetor that sprayed fuel under pressure rather than relying on gravity. At Packard, technicians adjusted jets and diaphragms to ensure the perfect fuel-air ratio under every condition. This meant pilots could slam open the throttle mid-dogfight, and the engine would respond instantly. No sputter, no lag, just raw power. Well, a powerful engine generates enormous heat. Without proper cooling and lubrication, the Merlin would seize within minutes. The cooling system used a water glycol mixture pumped through channels surrounding each cylinder. This absorbed heat and carried it to radiators in the Mustang's belly. At Packard, workers installed water pumps, radiators, and coolant pipes with leak-proof seals. The oil system was equally vital. High-pressure pumps forced oil through tiny passages to bearings, pistons, and camshafts. This thin film of oil reduced friction and carried away excess heat. Every pump was bench-tested to guarantee reliability. Then came the ignition system. The Merlin used dual magnetos, self-contained electrical generators to fire its spark plugs. Each cylinder had 2 plugs, doubling redundancy. Workers tested magnetos on specialized rigs, ensuring they produced strong sparks even at simulated altitudes. Spark plugs themselves were fired under pressure chambers to mimic thin air. A single weak spark could mean lost horsepower or even total failure. The Merlin produced incredible power, but that energy had to be harnessed efficiently. Enter the propeller reduction gear. If the propeller spun at engine speed over 3,000 RPM, the tips would go supersonic, wasting energy and creating shockwaves. The reduction gear slowed the propeller to about half engine speed, keeping it efficient while still producing enormous thrust. Machinists carefully assembled the hardened steel gears, checking clearances and lubrication. Any misalignment here would destroy both engine and propeller. Beyond the main engine, dozens of accessory systems had to be installed. Pumps for fuel and oil, generators for electricity, hydraulic pumps for propeller control, and more. Each accessory was mounted on brackets around the engine, driven by gears or belts from the crankshaft. Packard built these with modularity in mind, making field maintenance easier for mechanics overseas. Now all the pieces came together. On Packard's assembly line, engines moved from station to station. One team installed the crankshaft, the next added pistons, another timed the valves. Superchargers, carburetors, pumps, and magnetos followed. Each bolt was torqued to specification. Each gasket was sealed tight. At the end of the line, gleaming 27-liter V12 engine stood ready, stamped with Packard's nameplate and serial number. No engine left untested. Every Merlin was mounted to a dynamometer test stand. Fuel, coolant, and oil were connected, and then came the moment of truth. The first ignition. Engines roared to life, shaking the test cells. Technicians measured horsepower, torque, temperatures, and even fuel flow. Engines were run at full power for hours to prove their reliability. If anything failed, the engine was torn down and rebuilt. This grueling testing ensured that when a Mustang pilot pushed the throttle forward, his engine would deliver every single time. After passing inspection, engines were drained, sealed, and packed into sturdy wooden crates. Trains carried them from Detroit to aircraft plants like North American Aviation in California, where workers mounted them into Mustang fuselages. Within weeks, an engine cast and built in Detroit might be flying over France, dueling with German Messerschmitts and Focke-Wulfs. Only now, after walking through the factory, do we reveal the engine's origins. The Merlin was originally a Rolls-Royce design developed in Britain in the late 1930s. Early P-51 Mustangs used American Allison engines, which were good at low altitude but weak above 15,000 feet. The British tried fitting their Rolls-Royce Merlin into the Mustang, and the results were astonishing. The Mustang became faster, more agile, and capable of escorting bombers deep into enemy territory. The only problem? Britain didn't have enough industrial capacity to build Merlins for both Spitfires and Mustangs. Enter Packard. In 1940, the U.S. struck a deal for Packard Motor Car Company in Detroit to build the Merlin under license. Engineers adapted British blueprints to American tooling, and soon the Packard V1650 Merlin was rolling off production lines. By the end of the war, Packard had built over 55,000 Merlins, powering Mustangs, Spitfires, Mosquitoes, and even Lancaster bombers. There you have it, the heartbeat behind America's fastest World War II fighter. Swapping in the Merlin-powered Packard V1650 transformed the Wolverine-like Mustang into a legend of the skies. Some jet engines are so powerful they can launch a 600-ton aircraft into the sky with ease. Others are built to run for thousands of hours without missing a beat. Together, they've carried millions of passengers faster and more efficiently than ever before. In this video, let's count down the 10 strongest passenger jet engines ever built, starting with the least powerful all the way up to the most powerful passenger jet engine ever made. The General Electric CF6-80C2 is more than just an engine. It is an aviation icon that powered a golden age of long-haul travel. Developing up to 62,100 pounds of thrust in its B7F variant, this high-bypass turbofan became the trusted power plant for a trio of aviation workhorses: the Boeing 747-400, the 767-300ER, and the Airbus A300-600. Its success was built on a foundation of exceptional durability and reliability, making it a favorite among airlines for its low operating costs and ease of maintenance. The CF6 series' evolutionary design introduced numerous improvements in turbine cooling and aerodynamics, which significantly enhanced its fuel efficiency over previous models. For decades, the distinct whine of the CF6 was the sound of intercontinental flight, connecting cities across the globe and cementing General Electric's reputation as a premier engine manufacturer. The Rolls-Royce RB211-535E4 is the engine that gave the Boeing 757 its legendary performance, particularly on hot and high routes and transatlantic sectors. Generating a robust 60,600 pounds of thrust, it transformed the narrow-body 757 into a versatile and powerful aircraft, capable of operating from challenging airports with short runways. Its most significant and revolutionary feature was the incorporation of the wide-chord fan blade. These hollow titanium blades were a groundbreaking advancement, offering superior aerodynamic efficiency, reduced weight, and dramatically improved resistance to foreign object damage compared to the conventional solid blades of the era. The RB211-535E4's reliability and power made it the engine of choice for many flagship carriers, and its distinctive deep hum is still a recognizable sound at airports today. The Pratt & Whitney PW2000 series, particularly the PW2043 variant, delivering 43,000 pounds of thrust, represents a philosophy of intelligent design focused on overall efficiency rather than just raw power. As the competing engine to the Rolls-Royce RB211 on the Boeing 757, its advantages were found in its revolutionary lightweight construction and reduced maintenance requirements. It was the first engine in the world to enter service featuring a hollow, wide-chord fan blade constructed from a composite material surrounding a titanium core. This design provided exceptional strength and damage tolerance while shaving critical weight from the engine. Furthermore, the PW2000 incorporated a full-authority digital engine control system, which optimized performance and simplified pilot workload. The General Electric GEnx is a flagship engine of the 21st century, embodying a leap forward in materials science and efficiency. On the Boeing 747-8, the GEnx2B67 variant produces 66,500 pounds of thrust, but its true revolution lies beneath the surface. It is the successor to the incredibly successful CF6 and incorporates a host of technologies derived from the record-breaking GE90. Its most notable feature is the extensive use of lightweight carbon fiber composites. Both the fan case and the fan blades are constructed from this advanced material, making it significantly lighter and more durable than its predecessors. This weight reduction directly translates to a remarkable 15% improvement in fuel efficiency. The GEnx also features a simpler, more robust design with fewer parts. For instance, it has 30% fewer Stage 1 turbine blades than the CF6, which enhances reliability and reduces maintenance needs. The Engine Alliance GP7000 is a monumental achievement in collaboration, born from a unique 50-50 joint venture between aviation giants General Electric and Pratt & Whitney. Created specifically for the Airbus A380, the world's largest passenger airliner, its GP7270 variant generates a colossal 76,500 pounds of thrust. This engine is a masterful fusion of proven technologies from its parent companies. It leverages a core derived from the ultra-reliable GE90 engine and combines it with the innovative fan and low-pressure turbine design from Pratt & Whitney's PW4000 series. This best-of-both-worlds approach mitigated development risk and resulted in an engine renowned for its exceptional reliability and fuel efficiency. The GP7000 was designed with the A380's mission in mind: long-haul flights requiring immense power, whisper-quiet operation for passenger comfort, and redundant systems for ultimate safety over oceans. It successfully powered versions of the A380 for leading airlines like Emirates and Air France, proving its capability to lift the massive double-decker aircraft with ease. The Rolls-Royce Trent 900 was the exclusive engine for many flagship carriers operating the Airbus A380, including Qantas and Singapore Airlines, and produces 77,000 pounds of thrust. It embodies the British manufacturer's philosophy of combining immense power with refined smoothness and remarkably quiet operation. This focus on passenger comfort made it the perfect match for the A380, which was marketed as a luxurious, quiet giant in the sky. The Trent 900 benefits from Rolls-Royce's signature three-spool design, which allows the fan, intermediate pressure, and high-pressure compressors to each rotate at their optimal speeds. This architecture provides superior throttle response, operational flexibility, and improved efficiency across a wide range of flight conditions. Built with advanced materials and cooling techniques, it delivers outstanding reliability on the ultra-long-haul routes the A380 was designed to fly. The engine's durability and performance were so confidence-inspiring that it enabled record-breaking long-distance flights. The Rolls-Royce Trent 800 is the engine that certified the original Boeing 777 as a reliable and powerful long-range twinjet, with its Trent 895 variant producing a massive 95,000 pounds of thrust. Its development was critical to the 777's success, as it needed to provide not only immense power but also flawless reliability to meet the stringent extended-range twin-engine operational performance standards requirements for transoceanic flights. The Trent 800's three-spool architecture offered significant advantages, including a stable core resistant to stalls and surges, which was a key factor in building regulatory and airline confidence in twin-engine operations over remote areas. It competed fiercely against the GE90 and PW4000 on the 777, powering a significant portion of the fleet for airlines like British Airways and American Airlines. The engine's robust design and excellent fuel efficiency made it an economic powerhouse for airlines, capable of flying the longest routes with heavy payloads. The General Electric GE90-110B1 is a testament to relentless innovation, producing an astounding 110,100 pounds of thrust for the Boeing 777-200LR and 300ER variants. Before the 115B claimed the absolute record, this was the most powerful engine in the world, and its development was a monumental engineering challenge. Its most radical innovation was the use of composite materials for the massive fan blades. These blades are not metal, they are woven from carbon fiber composites, making them incredibly lightweight and strong, so durable that they can withstand the impact of a large bird. The engine's enormous size, with a fan diameter stretching over 10 feet, also necessitated a redesign of test facilities, as no existing cell could handle its power output. The GE90-110B1 demonstrated that such unprecedented thrust levels were not only possible but also reliable and efficient. The Rolls-Royce Trent XWB-97, generating 97,000 pounds of thrust, is the most powerful engine ever built by Rolls-Royce and the exclusive power plant for the Airbus A350-1000. It represents the pinnacle of modern engine design, where immense thrust is perfectly balanced with exceptional efficiency and environmental performance. It holds the title of the world's most efficient large civil engine in service, contributing significantly to the A350's claim of a 25% advantage in fuel burn and emissions over previous generation aircraft. The XWB stands for Extra Wide Body, referring to its large fan diameter designed to move enormous volumes of air for optimal efficiency. The Trent XWB incorporates advanced materials like ceramic matrix composites in the combustor, which can withstand temperatures that would melt traditional metals, allowing for a more complete and cleaner combustion process. The GE9X currently holds the world record for the highest thrust generated by a commercial aircraft engine, reaching a staggering 134,300 pounds of thrust during testing. Designed exclusively for the Boeing 777X, the GE9X is a technological marvel. With a fan diameter of 134 inches and composite fan blades is not just powerful, it's also efficient, boasting a 10% improvement in fuel consumption over its predecessor, the GE90. What's even more astonishing is that it manages all this while being the quietest engine in its class. GE9X is the future of high-thrust, long-range aviation, and when the 777X finally enters full service, it will carry this record-breaking engine into the next chapter of commercial flight. Few engines in history have ever combined such immense scale with such refined performance. So, which of these engines impressed you the most? Do you prefer raw power or futuristic efficiency? Let us know in the comments below. And if you enjoyed this deep dive into aviation tech, don't forget to like, subscribe, and hit that bell icon so you don't miss our next high-powered video. Thanks for watching, and we'll see you in the next one.